start with pole placement by state feedback. In this we will study introduction to pole placement, design of controller using pole placement, and we will see one numerical example. Now about the introduction to pole placement. Basically, what is meant by pole placement? Pole placement means that we have designed a controller. It is similar to the controller which we are designed in a classical approach. For example, in classical approach what we have seen, we have a plant just like this. Let us say this is controller C of S, then this is a plant G of S, and now this is feedback control system, it's negative, say RS and YS. First of all, why there is need for controller? A controller is needed because this is a plant GS, in open loop response is not satisfactory. Then without controller means without taking this into existence, we have taken a feedback control system, still performance is not satisfactory, and because of that we have designed this controller C of S. And we know that the classical controllers are P controller, that is proportional, then proportional integral, then PID, P, PI, PID, sometimes even a PD also. Other controllers are say lag and lead. These are the classical controller. So what is the problem with this controller is that as our purpose is to get a desired response result, whatever is the our objectives that need to be achieved. So we will find that if this GS or if the plant is of very high order, let us say 100 order plant, 100 by 100, or the GS the denominator order is say 100, denominator say order is 100. So in that case, if you design a PID controller, can we get the satisfactory results? Result means what? Let us say there are these poles are here, these are poles, and here somewhere these are two poles. Now here problem is that the poles which are nearer to imaginary axis that need to be shifted far away. So if you want to shift this using the PID controller, so what will happen? These poles may shift, this may shift, but what about these two poles? So it may possible that this pole may move like this or may move like this. There is no guarantees. Therefore, if you want the desired response or desired performance for higher order system, this is not possible by means of a conventional classical controller. So here we can use a state feedback controller. So what is the advantage of this state feedback controller is that you can place pole anywhere in the space. You can place pole here, you can place here, you can place here, then you can place here. Someone will say no, we want to place the pole at the juncture only, here. So this is possible because poles govern the performance. So you have a desired object that you can place the pole anywhere, it means that you can get a desired response, desired performance can be achievable. But there are some issues with respect to this. Problem is that if you move these poles, let us say original pole is at here. So the pole which is here, it has say a large time constant, but if you moving here this pole this side, so what is the time constant? Time constant is reduces, and when we are doing some measurement, because our approach is state feedback, state we have to measure. So when we are placing pole far away, where time constant is very small, we require high quality sensors, means accurate sensor, then we require the actuator, the large actuator, that is the motors. So all this involve more cost, and again there should be again we need to we have to make it available, sometimes it may not be available. Therefore, there is an issue about the pole placement. We cannot place the pole anywhere, although we can design theoretically. Practically there are some issues. Again the problem with this pole placement is that we have to measure all the states. If some states can't be measurable, then there are some issues. We cannot design a controller, although in future we will see design of the observer, but in actual practice if you want to design a controller, we have to measure all the states. And second, as we have seen that as we move the poles far away from the imaginary axis, then in that case we require a very high quality actuators. So there is the problem. Therefore, whenever we design a pole placement, first of all we have to see the requirement. Suppose if you have a pole at here, now let us say as -3. So if you know the pole at -3, if it at proper positions, so there is no need and to move this pole left side, because our requirement is satisfactory. That means you have to move the poles left side when there is a requirement. If you want to reduce some control energy, let us say one pole on the right hand side, this is 2, you can shift here at say -2. So if you make it like this, that is original system has pole as 2, if you move at -2, we require very less control energy. So that is some say thumb rule we can also use. Other thing which can be used, that because in system sometimes we require transient response, so we can place the pole, that is some poles are here, so that the transient issues will solve, and other poles we can place somewhat here on the real axis. So depend upon the problem, depend upon the availability, depend upon the cost associated, and mainly the availability. So we can design a controller, but the most important thing is that if we having the all facilities, everything is available, then in that case this pole placement is better technique than the classical controller. But in most of the times we do not have the resources. So in that case, that this classical control is far better, because in a classical control it depends upon the input RS and output YS, but whereas if you cover state space, we have to measure all the state which are involved in the system. Now we see how to design a controller using pole placement technique. Now we are designing the controller using pole placement techniques. So our system is basically x dot is equal to Ax plus Bu, this is our system, y equal to 6, and here we are designing controller because A is the system matrix. This system matrix A has pole maybe on the right hand side, it may have poles which are near to imaginary axis, that means this is the conditions. A matrix may have eigenvalues which are nearer, or it may possible that eigenvalue on the right hand side, that is system is unstable. So we have to stabilize this A, or we have to improve the performance of the A. Now if you draw the block diagram for this, so you will get now here is one integrator, now this is x, now here this is C, this is output y, now here is A matrix, now here x dot, this is x dot, now here is B, this is U. So you will find that for this case your plant is this x dot, that is equal to Ax plus Bu and y equals to 6. So this is a block diagram of the system. Now we have to design a controller. The controller we design, that means you have to design a control law, and this control law is through input. That means U plays the important role, how much input we have to provide, therefore U must be taken into considerations. And this u must have relationship with the controller. Therefore, the control law which we can consider as the control law which we can consider as u equal to say minus kcx plus r. This is a control law where this kc is belong to 1 cross n matrix, that is this kc is nothing but case k1 k2 up to say kn. So, this k1 k2 k1, that means this one k1 for one state, k2 for another state, kn for another state, because this basically related to the input and with the state, that is why the u equal to minus kcx plus r. So, this is the control law. Now, we have to use this control law in these equations of x dot equal to ax plus bu. Now, if you replace u equal to this in this particular equations, so we will get this x dot equal to ax plus this is b, u is minus kcx plus r. Now, if you solve it, so we will get ax minus b into kc into x plus b into r, and now if you solve it, we will get a minus b to kc into x plus br. Now, this is x dot. So, though this is the equation using the control law, whereas original equation is like this. So, now we have drawn the block diagram for this model. Now, as our system has changed, so u is coming to existence, our controller is coming into existence, therefore, our block diagram will change. So, now we read out the block diagram as, so here let us say this is integrator, C output y. So, here x dot, this is state x, this is integrator. Now, here this is a, this is b, and here as like this, this is r. Now, here positive, and now here we have got x dot equal to ax plus bu, and now what is this is u, you will find that this u equal to minus kcx, that means here we have to use a control law as this kc is the controller, this is negative and it is coming to this state x. So, if you see is x dot equal to x bu, where bu equal to this equations has been completed, and here y equal to cx. So, this is the block diagram of the system, and now it become a closed loop because the state has been controlled. Here there is no as such controlling effect. Now, we will see how to design a controller using state feedback controller approach, and whereas or we can say the control law which we are taking here u equals to minus kcx. So, here the plant which will take, suppose the plant g of s is taken as 1 divided by s raised to n plus a n minus 1 s raised to n minus 1 plus a n minus 2 s n minus 2 plus a1s plus a naught. Now, this is the GFS, but now here we are designing a controller for a system which is represented in a state space form. Therefore, the state space model of the system, it is in terms of x dot equal to Ax plus Bu, and therefore, here we will take this A matrix as, this A matrix we write in a companion form, that is 0 1 0 0, then here 0 0 1 0, and here this process repeated, it is still 0 0 1, and the last row we write A naught minus A1 minus A2 up to minus A n minus 1. This is A matrix, and now here B matrix is 0 0 say 1, and here this Kc is nothing but K1 K2 up to say Kn. This is controller Kc, A we have written B. So, here we are designing controller because the performance of this system is not satisfactory, therefore, we are designing the controller. So, here as per the control law u equals to minus Kx plus R. So, we have got the system matrix as A minus B into Kc. Original system matrix is A has some problem. So, the modified system matrix is A minus B into Kc. Therefore, here we can write down this matrix as A minus B to Kc, that is equal to 0 1 0 0 0 0 1 0, and here we get 0 0 0 1, and last row we write A0 minus A1 minus A2 to minus A n minus 1 minus B is like this 0 0 say 1, and here it has been multiplied by K1 K2 say Kn. Now, this we have to multiply, we have to subtract from this. So, after doing it we will get, so we will get as 0 1 0 0 0, you get 0 0 0 1 0, and lastly here 0 0 0 1, and in the last row we will get minus A0 minus K1 minus A1 minus K2, and here minus A n minus 1 minus Kn, because when this has been multiplied, this equation is nothing but 0 0 0 0 0 0, and last row will get K1 K2 up to Kn. Therefore, when we subtract this from this, you will get A0 minus K1, A1 minus K2 minus A n minus 1 minus Kn. Now, for this we have to determine the eigenvalues, because eigenvalues govern the performance. So, the eigenvalues of this system we can write down as lambda I minus A minus B into Kc, that is equal to, so we will get lambda raised to n plus A of n minus 1 plus Kn lambda n minus 1 plus A n minus 2 plus K n minus 1 lambda n minus 2, and this process repeated plus A0 plus K1. So, if you see the equations, so this is in companion form. So, once equation in companion form, we can directly write down the equation like this. So, lambda raised to n A n minus 1 K n lambda n minus 1 A n minus 2 K n minus 1 lambda n minus 2 A0 plus K1. Now, here this is the equation, this we want, but here we know the original system matrix A, But this k1, k2, k1 we do not know. So, they need to calculate this, then how to get it. So, here in this case we have to decide where we want to place the poles. So, we assume that our poles which are required to be placed, let us say, suppose the desired poles are at say lambda 1, lambda 2, say up to lambda n. These are my desired poles. So, it can place anywhere in the S plane. So, it has any values, but these are my poles. Now, if you base on the desired poles, we can also obtain the characteristic equations. So, using these desired poles, the characteristic equation can be written as lambda raised to n plus alpha n minus 1 lambda n minus 1 plus alpha n minus 2 lambda n minus 2 plus alpha 0 equal to 0. So, now this is the characteristic equation, this is our equations. So, these two equations are there, and here we will find that this is my desired one, and this they have the same form, lambda raised to n, lambda raised to n. These are the known quantities, and here a n minus 1, a n minus 2, a 0, these are known quantities, but which is unknown? Unknown is k1, k2 up to kn, and this is nothing but a controller. So, if we compare this equation with respect to this equation, there is two equations here, this let us say equation number 1 and let us say this is equation number 2. If we compare these two equations, we can easily get the values of k1, k2 up to kn. Now, we compare this equation. So, if you compare this equation, let us say alpha n minus 1, that is equal to a n minus 1 plus kn. So, if you solve it, we will get this kn equal to alpha n minus 1 minus a n minus 1, this we will get. Then about this alpha n minus 2, that is equal to a n minus 2 plus k n minus 1. So, after solving it, we will get k n minus 1 alpha n minus 2 minus a n minus 2, and now we come to this equation alpha 0 and this. So, if you compare this part, so we will get alpha 0, that is equal to a 0 plus k 1, and again if you solve it, we will get k 1 equal to, so here k 1 we will get, similarly we get k 2, k n minus 1 and k n. So, in this way we have got the controller as k 1, k 2 up to k n. So, this controller k will stabilize the system as per our requirement. As far as the simulation is concerned, you can design the pole anywhere, whatever we required, that desired pole placement is possible, desired controller is possible, desired performance is possible. So, this is the, we can see the beauty of the advanced control approach or a state feedback approach, where this is not possible in case of the classical approach. But although I told you that all the things theoretically is okay, but practically there are some issues. As I told you that we require high quality actuator, even the sensors, because we have to sense. So, if you are placing the pole far away, the control input is more, and that times it may got some problems. That means we required very high quality actuators. So, now this is the finally controller, and our main purpose is to design this controller k, and we have already designed it, but it has been designed through a mathematical approach, that is for nth order. Now, we will see how to get the value of the controller from a numerical example. So, we will solve a numerical example. So, the problem is x dot equal to ax plus bu. Now, here A matrix is 0 1 0 0 0 1 0 minus 3 minus 4 x plus b is 0 0 1 into u, and our desired poles, that is desired poles are at -2, -1, plus minus j1. These are our desired poles. You will find that the desired poles, in what way we have taken the desired pole, we have taken in terms of -1 plus j1, that is basically for the satisfying the transient issues, and -2 is the real poles. You can take desired poles as -1, -2 as well as -3 also, but in that case your system is completely overdamped, there are no transients. Sometimes for faster response we have to make this type of arrangement also. Now these are my desired poles, you can take other poles also, and now we want these poles. So what will be the value of the controller? So for desired poles we solve the equation as lambda plus 2 lambda plus 1 plus j1 lambda plus 1 j1 equal to 0, then here lambda plus 2 lambda 1 whole square plus 1 equal to 0. Now if you solve it, lambda plus 2 lambda square plus 2 lambda plus 2 equal to 0, and after solving it we will get lambda cube 4 lambda square plus 6 lambda plus 4 equal to 0. Now this is my desired characteristic equation. This is we have got, that is this is similar to our this equation alpha lambda raised to n plus alpha 0. So this equation we have got here. Now this is desired one, but when we using the control law, that is u equals to minus kx in this system, so we have got the equation in terms of a minus b into kc. So we determine this equation as a minus b to kc, that is equal to 0 1 0 0 0 1 0 minus 3 minus 4 0 0 1 k1 k2 k3. Now we have to solve it. So here we will get 0 1 0 0 0 1 0 minus 3 minus 4, and here after solving it we will get 0 0 0 0 0 0, and he will get k1 k2 k3. Now we subtract this equation from this, so we will get 0 1 0 0 0 1, because all are zeros. So after subtracting we will same 0 1 0 0 0 1. Here we will get 0 minus k1, that is minus k1, then here minus 3 minus k2, and here minus 4 minus k3. Now here a minus b into kc equation we have got. Now we have to determine this characteristic equation in terms of lambda. So lambda I minus a minus b into kc, so it gives lambda cube plus 4 plus k3 into lambda square plus 3 plus k2 into lambda plus k1 equal to 0. So this equation in the companion form, reverse way you see minus k1 minus 3 minus k2 minus 4 plus k3. So this equation we have got. So this is the equation we have got from the original plant, and in that case we will find that k1 k2 and k3 are there. So now this equation we have obtained, and now you see that this equation, this is the desired equations. Now we compare, let us say this equation number 1 and this is equation number 2. Now if you compare these two equations, so what we will get? We will get this k1 equal to, so just see what is k1 here. So k1 equal to 4. So we will get k1 equal to 4. Then about the another term, this lambda term, and here is the lambda term. So here 6. So this 3 plus K2 is equal to 6. So, here K2 equal to 3. So, K2 equal to 3, and about this last one. So, here 4 plus 4 into lambda square. So, here 4 plus K3 into lambda square. So, if you compare it, so 4 plus K3 to 4. So, we will get K3 equal to 0. Therefore, your controller K, it is K1, K2 and K3. So, that gives you 4, this K1, this K2 is 3 and K3 is 0. Now, this is the controller K. So, this controller K will stabilize the system in a such a manner that we are getting the desired performance. If you change the pole placement, you will get the different values of the K. Here we will find that this given system matrix, that is x dot equal to ax plus bu, that is in terms of a companion form, that is basically a transfer function form. And when the transfer function is there directly or when the system is given in the companion form, we can directly write the characteristic equations. There are no such issues. But when the system is in any of the general form, then these type of things, it is not easily possible. We cannot directly write down the characteristic equations. Therefore, we required some alternative method by which we can design a controller. That is our next aspect, is that how to design a controller when the given system matrix, say it is in a general form. And the other most important point is that whenever we design a controller, we have to check the controllability, observability of the system. Here we are directly design a controller, but actually when we design a controller for any system, we have to check the controllability and observability of the system. That means particularly this case, we will find that we have to basically implement the controllability, that is we have to determine B, AB, A square into B. So, all this operations is based on the rank of this matrix. If the rank of this matrix or the determinant of matrix, let us say 0, or when the rank is false, then this process, we cannot use this process, we cannot design a controller. So, controller will design when this QC is non-zero. And as I told you that this is the problem, or this analysis we have done only when you having a GS that is in a transfer function form. But now our main task is to how to design a controller when a given system matrix in a general form. So, that part we will see in the next class. So, now you see some references.